Think back to the early days of the web. Applications were straightforward. You had a single server holding a single, undisputed database. Whatever was written on that server was the objective truth. But a single machine only has so much memory and processing power. When millions of users flood a site, that single server reaches its absolute capacity. When the hardware maxes out, the entire system crashes and goes offline. To bypass these physical limits, engineers use a distributed key value store. Instead of one isolated machine, identical copies of the database are spread across multiple servers worldwide. Distributing data across multiple physical locations solves the capacity problem because you can always add more servers. But tying all these machines together relies on thousands of miles of cables, routers, and global infrastructure, introducing an unavoidable threat: network failures. This diagram shows a network partition, a loss of communication between nodes caused by a hardware failure or severed cable. Node N3 is completely cut off. If users write data to working nodes, updates cannot cross the connection. Node N3 is left holding stale data. This diagram outlines the CAP theorem. During a network partition, a system must prioritize either consistency or availability. You cannot guarantee both. Consistency ensures clients see the exact same data simultaneously. Availability ensures clients always get a response, even if nodes hold outdated information. Since network failures are a physical certainty, engineers cannot build a system with perfect accuracy and perfect uptime. They are forced to compromise, choosing a specific consistency pattern based entirely on what their users need most. When data accuracy is a strict legal or operational requirement, like checking your bank account balance, engineers choose strong consistency. A client is never allowed to see out-of-date financial data. Strong consistency enforces accuracy through quorum consensus. A central coordinator forces a specific number of nodes in the server ring to agree on a change before it finalizes. If the coordinator cannot guarantee enough acknowledging nodes have the latest data, the right is denied. The operational cost of this pattern is steep. If the required nodes cannot agree because of a network partition, the system intentionally blocks the user from reading or writing new data. It chooses to go offline. That loading error on your banking app is actually a feature, not a bug. The engineers are deliberately sacrificing your access to the app to protect your exact financial reality. Contrast that with social media platforms or retail catalogs. Freezing an entire platform because a single server in a massive cluster went offline would destroy user engagement and slash revenue. For these applications, systems use weak consistency. The network immediately accepts a user's update, like a new comment or a product review, even if subsequent reads from other users return old data, because the servers haven't synced up yet. The industry standard variation of this is eventual consistency. Given enough time, the system guarantees that all updates will propagate and all replicas will eventually match. This diagram illustrates the messy consequence of eventual consistency during a partition. Server 1 writes the location San Francisco to Node 1, while Server 2 simultaneously writes New York to Node 2. Conflicting truths now exist simultaneously on different servers. These highly available systems treat absolute truth as a secondary goal. They prioritize keeping you actively clicking and scrolling over maintaining perfect global synchronization. When the network reconnects, how do the servers figure out which piece of conflicting data is the correct version? This diagram displays vector clocks. Each edit gets a server ID and version pair. By checking pairs, the system proves if versions descend sequentially, or, like D2 splitting into D3 and D4, conflict simultaneously. Clients then merge these disparate paths back into a reconciled reality. Designing and managing this complex reconciliation math is the hidden tax engineers willingly pay. It is the cost of delivering an application that never appears to go offline. Traditional relational databases lock data down to guarantee strict accuracy. NoSQL databases embrace chaos, using vector clocks and eventual consistency to stay alive no matter what. There is no universal perfect database design. There is only a series of strategic compromises tailored to specific human behaviors. A frozen checkout screen blocking your purchase and a fluctuating like count on a viral post are both highly intentional consistency choices. The seamless internet is a manufactured illusion. Behind every digital action you take, an engineer has decided exactly how much truth you actually need in that exact millisecond.